having looked into the microstructure of steel and its the phase equilibrium diagram, now we can look into the use of steel in construction. However, we will refer back to the equilibrium diagram every now and then, because to understand some of the processes and properties of certain types of steel that we use in construction. So, general outline today we will be mainly discussing about the plain carbon steel, effect of alloying, we will discuss about cast steel, heat treatment, quenching and something about corrosion protection. Then we will discuss about selection of structural steel, and then followed by that something about cast iron. Lastly, some usage of steel in construction we will be discussing today. Okay. Now, structural steel, if we look at it, we are by this time we have become aware that basically stability is a major criteria. Therefore, design of structure is based on yield stress, right, that is useful stress. Beyond that there is excessive deformation. So, we do not use that stress. So, yield stress is a useful stress for us for our purpose of design. Also ductility, toughness at normal and sub-zero temperatures, weldability, these are other important properties. So, stress is the main thing in stress, but then we look at ductility, we look at ductility, we look at ductility, toughness at normal and sub-zero temperatures and sub-zero temperature, and that is sub-zero temperature, and that is our requirement for the steel. So, these are the properties which you require, right. Plain carbon steel has got good ductility and weldability when carbon content is low. Why it is so, we will try to see right now, and it has got sufficiently high yield strength when its yield strength increases when we have high carbon content, although I may not have ductility. We will see that, because both the things I cannot get together. If I get ductility, I do not get normally the strength, yield strength, high yield strength, and if I have high yield strength, then high ductility, then yield strength is low. You can recall that we discussed about strain hardening. In that case also we can increase by the process of strain hardening, we can increase the strength, useful strength, proof stress, etc., but its ductility gets reduced. So, even chemically, when we try to improve the yield strength, ductility gets reduced. We will see some of this right now. You see, this is the idea, plain carbon steel. If I look at it, if I have carbon content plotted along this direction, carbon content plotted along this direction, and is this direction I plot tensile strength. So, this axis is tensile strength and this is the curve. As my carbon content increases, tensile strength increases, right. Impact energy course starts reducing, because the stress strain curve, it will depend upon the stress strain curve, area under the stress strain curve. So, that is pretty high, but as I go high, strength increases, but impact energy reduces, because area under the stress strain curve is not anymore as high. Percentage elongation available, this is pretty high at lower strength, lesser carbon content, but as it increases, this reduces down significantly. So, that means my ductility reduces, and this is the hardness, right. So, this hardness also increases as I increase the carbon content. So, therefore, what happens? If you increase the carbon content, strength increases, tensile strength increases, hardness increases, but percentage elongation available at failure, that decreases and impact energy decreases. So, that is what you increase carbon, it becomes brittle. If you have low carbon, then of course, yield stress or tensile stress is relatively low. So, that is what the idea is, and therefore, what we do is we actually restrict it to 0.25% maximum in case of mild steel, which you use usually for construction very often. So, effect of carbon content on mechanical properties we have seen, and we see that we restrict it to 0.25% maximum for the ductility requirement. That is what finally comes to, if you increase carbon content, strength increases but ductility reduces. And then we define the useful strength in terms of what is called 0.2% proof stress. We might have stated this earlier, but again let us repeat, right. And this looks like this, because whenever your stress strain curve does not have a sharp yield point, we can't use, we do not know what is a useful stress that I can use, because beyond a point, as you can see in this diagram as well, beyond a point actually this is it is plastic, it shows plastic deformation. So, which point shall I use for my useful strength or useful strength? So, we define it in terms of 2% proof stress, and that would look something like this. 2% proof stress will look like this. What I will do is, I draw a line parallel to my stress strain curve at 0.002 strain, at 0.002 strain, at 0.002 strain. This strain is 0.002, 2%. So, 0.002 strain, draw a line parallel to the stress strain curve, that is the elastic portion of the stress strain curve, and wherever it cuts, that is the 2% proof stress. I can have 1% proof stress or 2% proof stress. So, that corresponds to 0.002 strain, drawing a line parallel to the stress strain curve, linear portion of the stress strain curve, right, I get it. So, that is proof stress, and of course, we know that most of our plain carbon steel will have modulus of elasticity 200 GPa. So, let us see alloying effect on plain carbon steel. What we have seen so far, carbon increases strength, but ductility reduces. But in steel, while you are producing, there are several other elements which comes through the process. Of course, we do not add them, but several other elements which comes through the process, and we control their percentages. Specification of the steels will say this much should not be more than this, or that kind of thing, or ranges of the percentage of this material that should be there is actually specified in most of the time in the codes. So, for example, manganese, it arises from the process and it increases the strength, both yield and ultimate strength, but reduces the weldability. So, therefore, its percentage again is restricted in the relevant code. Sulfur increases brittleness, induces fatigue, and this also arises from the process, because iron ore, when you are getting, or in the process you might be adding something which will bring in this into the steel. So, this is there, it comes from the process actually, and its percentage is actually controlled to 0.06% maximum, because it increases the brittleness and induces fatigue, lowers down possibly fatigue strength. Phosphorus increases strength, also increases corrosion resistance, but decreases ductility, and it also arises from the process, and it is maximum percentage is 0.06%, specified maximum percentage is 0.06%. Silicon improves strength, but excess can reduce strength, as carbon then occurs as graphite flakes. Silicon also arises from the process itself, we do not add them intentionally, but they are there, and if you add too much of silicon, then the carbon becomes graphite and graphite flakes, and whereby it actually reduces the strength. So, excess but improves the strength, excess can do this. Niobium and nickel increases strength, copper increases corrosion resistance and reduces ductility, chromium increases hardness and corrosion resistance and reduces ductility, and these are the effect of various kind of alloying in plain carbon steel. So, let us look at cast and overheated steel. Certain processing we can do through the plain carbon steel, and we will see that they will enhance the property or kind of change the property and make them useful from different way. So, let us see what are those. Let us see what is cast steel. Now, cast steel deals with the situation where actually the steel is coming from the liquid molten state. That means, it is coming from this topmost place, it is in liquid, and then we are dealing mostly with the situations where my carbon content is less than 0.85, the point E that I mentioned the other day. So, it is less than 0.85 because the steel having more than 0.85 percentage of carbon is not really much useful as far as civil engineering construction is concerned. They have there of course other use in tooling etc., but in civil engineering we are dealing with mostly low percentage of the steel with low carbon percentages, besides of course cast iron which is higher, which we will discuss separately. So, if you come here, this you know our if you come here, here you know this is the liquid state, and then you have a cast steel is produced by cooling it from these situations, and let us see what happens. You see, steel with carbon less than 0.85% when cooled from liquid state, they solidify to form coarse grained structure, austenite. You know, this is austenite, if you remember, if you recall our last class discussion. So, you will first you will have austenite and liquid, and then of course, below 8.5 you will have austenite formation, and A3 line, up to A3 line it will be all austenite formation. If you cool it further beyond A3 and go to A1, you know, here the combination is ferrite plus austenite, if you remember again from our previous discussion. So, alpha this is ferrite and this is austenite. So, combination of ferrite and austenites forms, and then here the ferrite will start separate at the boundaries within the austenite grains and continues till A1. So, till A1 what will happen? You know, if you come from here first liquid, then you have come somewhere here, it is all austenite formation, and then as you come down to this A3, beyond A3 at the austenite grain boundaries, ferrite will start separating out, and that will form till A1. And if we go further beyond this, then what will happen? Well, we will continue with this, and we can see that on cooling below A1, that is this line cooling below this line, pearlite containing finely laminated ferrite and iron carbide forms. Now, in this region you have got ferrite and cementite, which is iron carbide, right. If this is what it is, and this is called pearlite. So, it has got, when it has got a finely laminated structure, laminated ferrite and iron carbide forms, they are in alternate laminations of ferrite and cementite, right. That has got a look of the pearl, that is why they are called pearlite. With below 8.85% this pearlite formation would take place. The final structure of the cast steel therefore is relatively coarse structure of ferrite and pearlite. Now, this has got a coarse structure, laminated, because the grains that has formed, that is not very fine, and it has got a coarse structure, and that is formed, and that is ferrite pearlite is the structure of the mild steel below 0.85, plain carbon steel below 0.85% of the carbon. You can get a similar structure known as overheated structures when you heat it up at this region, when steel is heated for a long period in high temperature in this region and permitting the grain growth to occur. So, this is cast and this is called overheated steel. So, cast steel will look like this, it will have a ferrite pearlite structure, and what is pearlite? Pearlite is essentially ferrite, and I mean it has got alternate laminates of ferrite and cementite. So, this is what you will have, because alpha is the ferrite plus carbide, this together, this is what you get in mild steel structure, and one can see this under microscope, the structures can be observed, right. So, that is what it is. Let us see what happens when you treat the steel, heat treatment of the steel, right. So, supposing I have this steel, same ferrite pearlite structure, and now I heat it up, right. So, if I heat it up to say first A1 and then to A3, this pearlite up to this is of course A1, nothing will happen, because it is same structure, and beyond A1 what will do? What will happen? Pearlite will change to austenite at many nuclei within the pearlite structure and form a very fine grained structure. So, when you are cooling it, cast steel, that has got a coarse structure of ferrite pearlite. When you heat it again, let us say, and go beyond this point, go beyond this point towards A3, the pearlite will change to austenite, and since it starts in austenite formation starts in many places at many nuclei, what will happen? You will have a fine grained structure. At many locations it will start, and within that pearlite structure itself and form a very fine grained structure, right. It forms a very fine grained structure. Okay. Then again, let us say we cool it back. So, we have heated it, and if we cool it back from A1 to A3, ferrite separates at the austenite grain. So, now we have had very fine grained austenite structure forms, and when I am cooling it back, this austenite would tend to start again forming ferrite, and at the grain boundaries, because the fine grained structures. So, in the fine grained structure itself, and at A1 all remaining austenite changes to pearlite, and because of fine grained structure, both strength and ductility is higher compared to castile. If you remember, we said that when I have got fine grained structure, then its strength increases. So, therefore, in my castile actually did not have a very fine grained structures. Now, with this heat treatment, I can get a fine grained structure, and therefore, what we can see is on heating beyond A1 to A3, pearlite changes to austenite and benenuclei within pearlite structure and form very fine grained structure. So, that is very important. On cooling from A3 to A1, that is what we saw, ferrite separates at the austenite grain boundaries because of fine grained structure. And at A1 all austenite changes to pearlite because of fine grained structure, and both strength and ductility are higher compared to castile. So, that is what it is. So, heat treatment gives you a better structure in terms of fine grained structures, and therefore, its strength and ductility is increased. Let us see some other process through which we can change. Now, this is one thing. So, I increase the strength and ductility, but I might like some time to soften it out for machining. Now, those processes which are involved are called annealing and normalizing. Now, remember we talked of annealing in the case of strain hardening. If I want to relieve the stress of strain hardening, what I did annealing. I heated it up beyond recrystallization temperature, and when I cooled it, it recrystallized, and all the history of strain hardening was lost. Well, this is different. This is not, we are not really looking at the stress relieving. So, annealing is the terminology used in both cases. Here it is used not to the strain hardened, but to simple plain carbon steel, right. So, besides stress relieving in cold work steel, annealing is the process which softens the steel, and normalizing also does the same thing. Normalizing does the same thing. Let us see what this process are. Let us see what this process are. The steel is heated above line A3. This line is A3 line. If you remember, just in the background, same equilibrium diagram I have, because we are repeating. So, this time I have put it in the background, if you can recall. So, A3 is here, and right, and it is heated above A3 temperature and held to attain uniform temperature and uniform composition. So, you heat it up beyond A3 line, and we are discussing all steel with 0.85, less than 8.85% steel, I mean 85% carbon, and you see, if you heat it up for sufficient time, so that it becomes uniform in structure and also in composition. So, all grains become actually austenite, right, composition, and then cooled slowly in the furnace. So, when you cool it slowly in the furnace, that is what is actually annealing process. It actually, in this process, you will get actually a coarse grained structure resulting in softening of the alloy or metal. Normalizing is similar, except that cooling is done in steel air instead of the furnace, and therefore, it is a cheaper process, and it has got slightly finer grain because of faster cooling. So, since this cools at a very slower process, the grain formation will be coarser, and in this one it was cooled in furnace. So, you will have a very slow process of cooling, and that is why you get a fine grained structure, right. You get a fine grained structure, and we come from A3 to below, that is what it is. So, essentially the steel heated above A3 temperature and held it to attain uniform temperature and composition, then cooled slowly in the furnace. So, normalizing, we put it in steel here and do the same thing. What does it do? Its effect is both annealing and normalizing results in increasing softness, because now we have a coarse grained structure. So, therefore, it is soft, it is not strong, and how does it help? It helps us machinability of high carbon steel, it helps us in machinability, you can cut or machine it easily. Last, normalizing one, that is the last one out of the two, is economical and less, because we put less time in the furnace, but it has got slightly fine grained structure. So, we process steel by hot rolling process, and hot rolling slightly above A3 temperature results in a very fine austenite grain structure, and on air cooling product similar to normalizing in obtain. So, when you hot roll slightly above A3 temperature results in very fine austenite grain structure, and then when you cool it you get something product similar to normalizing we get. So, hot rolling gives us this kind of product which is machinable. Right. Structure of slow air cooled steel up to 0.85 degrees 85% carbon is similar, and one important issue I would like to tell you is the proportion of perlite is same as proportion of is similar is proportional to actually proportion of perlite is proportional to percentage of carbon. Proportion of perlite is not same, but we can say proportional. It is not same, but it is proportional. It is actually proportional proportional to carbon percentages, that is when carbon percentages vary from 0 to 0.85%, 0 to 100% perlite. So, at 0.85% carbon you have 100% perlite present, perlite is 100%, and if you have less percentage of perlite will change accordingly in the structure. So, from the percentage of perlite in the structure of the steel you can find out what is the percentage of carbon indirectly. So, this is what it is, this is what it is, right. Right. So, then look at another process how we change or improve the properties of the plain carbon steel. The process is known as quenching and tempering. The process is known as quenching and tempering, and we will see some of them are very important for us. Last lecture we discussed about strain hardening, which is very important, and now we will see that this is very important because we use many of the reinforcing steel based on both these principles. Now, what is quenching? When small section of steel are quenched with water, are water quenched to form austenite or gamma region, right, quenched from actually austenite region from gamma region. The cooling rate is too fast to allow separation of ferrite and formation of perlite by the nucleation of growth process. What we are doing, we had if you remember in this austenite region, gamma region, I heat up the the steel, or even if it is cast steel I am producing, from cast steel I am producing, when I am producing it at rolling mill, what I am doing? I am now quenching it at a very rapid cooling, quenching with water, therefore, actually it is rapid cooling, very rapid cooling takes place. Now, this cooling becomes so fast, that it does not allow separation of the ferrite formation, right, from separation of ferrite and formation of perlite is not possible. So, below from this region if I am cooling it here, this formation of ferrite alpha and then formation of perlite is not actually becomes possible, because nucleation and growth process is hampered, right. This is not, this is restricted. So, what happens? We know that this is actually face centered cube, this is face centered cube, the austenite, and it should become body centered cube. Now, we are cooling it rapidly, and at such condition face centered cube austenite is unstable, but it does not have time to get quickly converted into body centered ferrite structure, but since it is unstable it cannot be prevented also. So, something in between happens, something else happens, and it is actually some sort of body centered cubic formation takes place, but this takes place by shearing mechanism, where planes of atom move to give body centered tetragonal structure, which is not same as the ordinary ferrite, but it is a kind of elongated in one direction, right, elongated in one direction. So, it is not same as the original, because now it is cooling rapidly. So, the original structure formation is hampered, the nucleation and growth process cannot take place, but when it is cooling, when it is cooled, actually the austenite structure is not also stable. So, it tends to form something which is different than the conventional body centered cube ferrite structure. It is a it forms a body centered cube, but it has got slightly elongated, it is slightly elongated in one direction. So, that is what happens when we are trying to come from this, right, and the result is of course, we can see that result is C atom remain, of course, it remains and it goes into interstices, it goes into the interstices, all right, forms a solution, right, but it is in a supersaturated state. So, it forms a supersaturated interstitial solution, and the structure is known as martensite, which is extremely hard and brittle owing to the distortion produced in the lattice, because now the lattice has become distorted, and owing to this distortion the structure is extremely hard and it is also brittle, it is extremely hard and brittle, right. So, quenching produces an extremely brittle and hard structure called martensite. All right. If I heat it below, if I reheat it now, that would what would form just if I leave it like this. But supposing I reheat it below or reheat it below and then what will happen, the iron carbide forms in globular form. So, when I reheat it say up to 200 degrees centigrade, the retained carbon precipitated as iron carbide. Carbon that was retained, it precipitated as iron carbide in globular form at temperature 200 degrees centigrade. And this globule size increases with temperature and may give strength and ductility superior to normalized steel. At lower temperature, slight less hardness, but toughness increases. So, if I reheat it up to 200 degrees centigrade and above, the carbon which was there, it gets precipitated into a globular form, and that gives you higher strength. If I reheat to slightly higher temperature, I still get higher strength, but if I do it at a slightly lower temperature, of course, I will get slightly less strength, but still it will be much higher than the normalized steel. So, that is the idea, and that is the idea of quenching and tempering. So, first I do quenching, cool it rapidly, and if I reheat it, it would behave like this, right, it would behave like this. Well, similar sort of effect I can get. First I quench it, but then do not reheat it, but allow it to actually cool it slowly or temper that portion that is temper it by retaining the heat, slowly allow it to cool slowly, so that it remains tempered. It does not, first you cool it quickly, then you reheat it in a way, and cool it and then reheat it, and that is what you get it. Okay. So, by tempering process, that is what you get, right. So, this is the process of quenching and tempering it will be useful, as you shall see. Using this process, actually we get what is called thermomechanically treated rebars. We will discuss this sometime later on in one of the lectures, right. So, let us see how we get ductile and stronger steel. Reduce carbon content and increase manganese content with progressive reduction of carbon content gives ductility. So, if I want to get ductility, manganese is used to get ductile steel, and then if I want to get stronger steel, decrease in ferrite grain size gives increase in both tensile strength and yield strength. This is one issue. The other way is to high yield strength is achieved by lower ferrite grain size and reduction in pearlite. So, if I reduce pearlite, that is low carbon, I get high yield strength, and therefore, if I combine this aspect, reduced carbon content reduces pearlite and small amount of vanadium and niobium reduces grain size. We talked about niobium earlier and niobium and nickel. So, this niobium is actually able to reduce the grain size, and vanadium also able to reduce grain size. So, I reduce the grain size, lower carbon content, my strength increases. So, it is one of the ways of getting stronger steel. Of course, the processes we have seen, with certain processes we can get stronger steel, right. So, what we have seen in case of plain carbon steel, generally of course, we use mostly mild steel, which is less than 0.25% carbon, and normalized steel quite often we will be using, because we need also machinability, etc. So, that is what we do, and normalized, we normalize steel quite often we use for structural purpose, and that is what most commonly used, but this special type of treated steels are used in fact more in rebar, and when we discuss about rebar we will see their utility, some of those special steel. Of course, in special places again special steels are used. So, when you see some usage, for example, pre-stressing steel or cables, suspension cables, we will discuss about their steel, and this whatever we have discussed so far will give us a proper understanding why we use those kind of steel in such situation. But one major problem with steel is of course is susceptibility to high temperature, because we know that when susceptible to high temperature, steel cannot withstand, its fire resistance are relatively much poorer compared to concrete, and therefore, you usually what we do, we actually cover the steel up with concrete, encase it in concrete, or sometimes we put it in gypsum boards or water filled column, etc. So, this is one usage which of course we discussed in the connection with fire protection. So, gypsum concrete infield what you call enclosed column steel or steel structural members are used to take care of fire protection. But the other issue is of course is corrosion protection, and let us see what we do related to corrosion protection. Corrosion of course in steel, when you are looking at it, it can be dry corrosion, and this occurs at high temperature, but that is not much of our interest. But we know about wet corrosion, and we know that it is electrochemical process. We have discussed it at length in the connection with rebar corrosion in concrete. Here we will not discuss the corrosion process, but we know that it is there and it is electrochemical and occurs in electrolyte. What we do to protect against corrosion is protective coating of paint, aluminum or zinc, or any various kind of protective painting, organic or epoxy paints or various kind of paints, or aluminum or zinc coating we do apply. We can use cathodic protection, whereby what we do is we actually, since we know that corrosion is an electrochemical process, we apply current from outside, what is known as impressed current system, such that it neutralizes the effect of the electrochemical corrosion current. Also, a second method could be make your steel a cathode instead of anode, because we have seen at anode the metal dissolves, at cathode of course some other reaction takes place. Supposing I put a metal which has got more corrosion tendency than the steel itself and connect it together in my structural system, then that metal itself will corrode and protect the steel. So, that is called sacrificial anode. Details of this is not of course in the scope of our discussion, but cathodic protection is a measure used as a regulation practice in buried steel pipe, and where we use or even in offshore structures. So, where we use actually sacrificial anode such as aluminum, because it is relatively cheap. Remember that process is fairly costly, because in sacrificial anode from time to time the anode that has been sacrificed, that is aluminum anode which has become anode, which we connect to the steel to protect the steel, make steel cathodic, the aluminum will be consumed with time, and then you have to replace it. So, this is a costly process, and one has to monitor also the corrosion quite often. In impressed current you can have battery operated current circuit current so you apply through an auxiliary electrode a current into the structure and protect it by opposing the electrochemical corrosion current. So, this is cathodic protection, but again discussion on this is not really in the scope of our lecture. Detailed discussion, we just introduced this to you. Coatings forms a barrier. I just would like to give you some more information about this coating. Coating forms barriers, aluminum or zinc coating, galvanizing zinc coating is applied. Now, these ones when applied, they form their own oxides right quickly, they form oxides at the surface of the steel and provides a barrier for further corrosion to take place. Addition of copper and some other alloys like chromium, stainless steel, it's other chromium, high percentage of chromium. So, this they do not corrode so easily. Well, but stainless steel cannot be used in structure except in exceptional cases, because it is very costly, relatively very costly. But in exceptional cases one may use even stainless steel which does not corrode, because it is the exposure condition which will dictate this use. So, that is about corrosion protection. Increased amount of phosphorus chromium forms protective oxide against corrosion, as I said. So, all this forms corrosion protection, forms kind of protective coating, because they themselves form oxides, and this oxides actually forms a barrier between the outside environment and the steel, and thereby protects the steel. But remember, maintenance of steel is relatively costly, because you have to paint from time and again. When it is lost, again you have to paint it to protect it. After all, steel is produced, it is in nature not available in iron, is not available in metallic form, pure metallic form. It is actually in form of pyrites or oxides. So, therefore, it will have a tendency to get converted, and we produce iron at the expense of considerable energy. So, it will like to dissipate this energy, we raise its chemical potential, in other words. So, it will like to dissipate that energy, come back to the normal state of its potential, and therefore, iron will have a tendency to form oxides. So, we protect them, rate of this oxidation we reduce, that is what we said when we discussed about the rebar corrosion also, and that is what we like to reduce it down, and that is why you have to maintain maintain it through painting or whatever cathodic protection, but it is a costly process. And this is one reason why it has not been used in countries where concrete is cheaper, but by nevertheless steel is also equally useful material for us. Not only that, in concrete you can't do without steel reinforcement really, as we shall see in our next lecture, that steel is the best reinforcement till date. Okay. So, that is what it is. Following up corrosion protection, some of the detailing can improve your corrosion protection very easily. For example, do not allow dust to accumulate, or water or dust to accumulate. So, if your structure is something like this, dust gets accumulated here, right, and if it is something of this kind, so detailing of the structures, then dust cannot accumulate here, right. So, dirt collection should be avoided. So, pay attention to dirt collection. For example, if there is a tray, trough like situation here, or a tray where dust can collect, if it is other way around, then you can, if you seal it up actually, then this dirt cannot collect. So, dirt collects, it will attract moisture, both moisture and oxygen is available, corrosion will proceed. Actually, corrosion is a phenomena where presence of water and oxygen is masked. So, if we can keep the structure both moisture out of it, and oxygen obviously you cannot keep out, but moisture out of it, it would actually ensure that there is no corrosion. Similarly, you have something like this, right, you have something like this, and something like this where water can actually air movement will be relatively less. Here, if the air movement is available in this particular one, this one was like this, you see this particular plate was something like this. Now, here this allows for air movement. So, if air moves, the moisture will go away, vapor cannot deposit, and therefore, corrosion protection will be there. In fact, what you have done, you have provided a gap between this top, this was actually connected, completely joined here with a fillet weld, as you can see. Now, if you leave it slightly up, so air can move easily, and therefore, no moisture, no air, and air movement will ensure that there is no moisture vapor condensation here, and drying off is easy, and therefore, corrosion, it will protect from corrosion. Similarly, if you see, if you provide a sort of drainage break if you provide, instead of this drainage break if you provide, then water will not really penetrate, water will not stick here, and corrosion will be, prevention of corrosion is possible. So, these detailings are important as far as steel is concerned. For example, this is bad, which will allow water to come in, this is better, no water can penetrate, and this is the best. So, if there is no water can actually accumulate here, this will have bolted. So, water will accumulate here, and therefore, corrosion will proceed. It is welded in between, water can still go in, but if this is jointed together, that is best. So, by detailing even you can improve the corrosion protection in case of structural steel, as you can see here. Right. This is important to avoid corrosion. How do we select then structural steel? Strength is the main requirement, as we have seen. Strength of steel is mainly requirement. Then corrosion is an important issue. We have to see, because steel you can't, steel, iron will always corrode, thermodynamically will always tend to have form oxide. So, we will have to see that environment, exposure condition is very, very important. So, exposure condition is important, availability is important, ductility and other mechanical properties are also equally important. Other mechanical properties are also important, strength and other mechanical properties, availability, exposure condition, protection against corrosion, etc. Which steel is available? Supposing a steel is not available, you can't use it. So, availability will be one of the major factors which will govern what is our requirement, what steel I am going to use. Exposure condition would decide again what steel I should use, because if it is a highly corrosive, aggressive environment, then you have to choose steel accordingly. So, that is, and mechanical properties overall. Right now, but I have mentioned that fire properties of steel is not as good. So, you normally use encased. You can have better improved fire steel with improved fire resistance today. Advanced steels are there which have got better fire resistances, but it is one of the drawbacks of the steel. So, we normally structural members used in buildings and similar situation where susceptible to fire or fire hazard, what we do in encase the steel in either in concrete or in either in concrete or in either in concrete or in gypsum. I will just like to give you the example of this one. I like to give you example of this one, because if this is my steel section, let us say if this is my steel section, it is a I section, let us say I section, let us say this is my I section, right, this is my I section, let us say steel section. So, what we do is we make concrete encasement here, we encase this in concrete, right, encase this in concrete. So, provide fire protection, or we can encase this in something like, gypsum board. You can put gypsum boards here, gypsum boards, because we have seen that earlier, one of our earlier lectures, gypsum is a very good fire, has got very good fire resistances. So, I can provide gypsum boards here or encase them in concrete. Sometimes we have what is known as water filled column. For example, the column systems, like this is the channel, this channels made into box, right, this is the channel section. So, this is used in very tall buildings, this has been used. So, channel section, you have water here, you have water filled columns, and such columns, all of them will be connected together, and you have a vent at the top for evaporation, etc., etc. These are used in very tall multi-story buildings. So, wherever there is a problem related to where you expect there is a fire hazard is there, in that case you use steel with encasement, or you use steel encased steel members, or use actually provide encase them in concrete or in gypsum. So, that is the kind of fire protection measures we use for steel, right. Okay. So, cast iron is one of the steel that is used. We have talked about ductile and slightly high strength steel, and then cast iron is another product which is used of the iron carbon system, FEC system. This has got 2.5 to 4.5% of carbon, and it depends upon its its property depends upon cooling rate and presence of silicon, etc. There are two types of cast iron, grey cast iron, and the name comes from the color of the fractured surfaces, right, and it is produced by slow cooling, generally used in piston rings, etc., etc. You have graphite present in them, and white cast iron will have carbide, and it is produced from rapid cooling, and the color of the fractured surface is white, and that is how it is, the name is, right. So, this is also used. Cast irons are anti-corrosive, again they have high resistance to corrosion. So, used in waste pipe, sewer pipes, and so on. Some pipes, CI pipes are quite commonly used, although these days of course they have been replaced by and large with the polymeric PVC and similar other pipes, right, polymer or plastics pipes, but this has been used very much, they are in use. One issue is weldability is one of the major property, and we see that weldability we can find out through what is known as Grabile's diagram, and this looks like this, right. Now, this reduces with carbon and alloy element. as I will explain this diagram a little bit later, but let me just look at this. The more the alloying element I add into the iron, weldability reduces, and we have something called carbon equivalent, which is plotted on this direction. This is called carbon equivalent, which is plotted along this direction, and carbon equivalent is defined C plus manganese plus silicon divided by 6, chromium, molybdenum, vanadium divided by 5, and nickel and copper divided by 15. So, this is your carbon equivalent and this side is your carbon. Carbon equivalent is obtained by this equation and this is your carbon. So, as I increase my carbon equivalent percentages and carbon percentages, this line is 45-degree line, because carbon equivalent has C plus something. So, this will be always greater than the carbon percentage. So, this zone is infeasible zone, this zone is infeasible zone, this zone is weldable, this zone is difficult to weld, and this is readily weldable. So, what we see is, as my carbon equivalent increases, along this direction for a given carbon content, let us say this carbon content, this becomes difficult to weld. So, reduces with carbon and alloy content, weldability reduces with carbon and alloy content, right. So, this is weldability of plain carbon steel. Let us discuss some quickly before in this lecture, discuss some of the usage and some of the steel that you use in cases like pre-stressing steel. Now, what are the desirable properties of the pre-stressing steel? It must have high tensile strength. When do you use pre-stressing steel? I might have discussed or mentioned this sometime in connection with the concrete. Concrete is weak in tension, it is brittle. So, to improve its tensile load carrying capacity, we either reinforce it and then use a composite called reinforced concrete. The other way is to you pre-stress it using some steel. So, what you do? You pull the steel wires or strands or whatever they are, and then anchor them into the concrete, something like this. It will look something like this, pre-stressing would look like this. We might have seen it before, but still let me just let us recall this. You see, it will look like this. Let us say if this is your concrete specimen, just let us say a beam element, then I pass wire through this. A simple case, let us say I pass the wire through this and I pull it. After pulling, I anchor it up here. Simple case, I anchor it up here. So, when I anchor it up here, what will happen? Since I have already pulled and given some strain to it, maybe elastic within the, it is within the elastic range. So, what will happen? It will try to shorten, because I have pulled it up, put some stress onto it, and then it will try to, now this will try to actually shorten, this will try to shorten. When this is try to shorten, this will actually apply a compressive force onto the concrete. So, the concrete is initially under compression. Now, when we actually apply tension to the concrete structure, apply tension to the concrete this structure and cut off this, snap off this wires. So, I have a composite section where I have a pre-stressing wire which has been pulled, and through its anchor this concrete is being compressed, So, it is under pre-compression. So, if it is pre-compression, this is the compressive stress, then I apply some tensile stress, this is 0 stress, this is 0 stress, this is compression, and this side is tension. So, I apply some tension on this side, it will neutralize this compression and will be able to withstand this. So, a pre-stressed concrete member will be able to withstand certain amount of tensile stresses, because concrete itself is weak in tension. So, by pre-compressing it, I can make the concrete system to actually withstand some amount of tension, and flexure etc., details is of course not really a part of our discussion at the moment. So, pre-stressing is that I actually pull the steel and it should have then high yield tensile strength, so that high elastic strain can be induced, right. So, high elastic strain can be induced. Now, we mentioned about creep relaxation in case of concrete. So, this under load, if it is deforming, so I have pulled it up, and if there is a creep and it is deformed more, there will be some amount of relaxation. We have seen that in restrained situation there is relaxation in case of concrete, same thing happens in case of steel also. So, this should have low creep relaxation, otherwise the pre-stressing loss would be there, high pre-stressing loss will be there. So, these are the property desirable of pre-stressing steel. It should have a good bond with concrete for pre-tension case that I have talked about is a pre-tension situation where you cast the concrete after over the pulled pre-stressing wires or strands. First pull the wires and cast the concrete just over it. So, the compression from the pre-stressing wire to the concrete is transferred through bond. So, where it is transferred through bond, I need a good bond strength also. Therefore, these are the desirable properties. So, what kind of pre-stressing steel we use? Its carbon content is 0.629%, often cold drawn, work hardened, cold drawn to increase its tensile strength, right. Carbon content is this much. Tensile strength might range from 1570 MPa to about 1850 MPa. Maximum relaxation is 3 to 8.5% at initial stress of 70% characteristic strength. So, this is the property of the pre-stressing steel we desire, and that is what is a that is why we have carbon content this, and then strengths are something like this. It is cold drawn, usually cold drawn. Heavily galvanized, high strength, toughness and fatigue. If you are looking at cable suspension, bridges cable, this is another kind of steel which has to withstand high tensile strength. It stresses, high tensile stresses, that is, it must have a high tensile strength. Suspension cable of cable suspended bridges, but they are exposed to also corrosive environment. So, therefore, they are heavily galvanized, high strength, high toughness, right. They should be able to withstand a lot of fatigue, because there will be horizontal movement due to wind. Suspension bridges cables are they have to there are a lot of sort of horizontal movement of the deck. So, it has to withstand stresses related to this swing of the deck, etc., etc. Therefore, it must have a lot of toughness or impact, it has to withstand good fatigue resistance, because reversal of stresses would be there, right, because not only because of the load onto the road or the deck, but also because of the wind forces. So, we need high strength, toughness and fatigue resistance. Therefore, cold drawn with this much 0.75 to 0.85% of carbon and 0.5 to 0.7% of manganese, because this will increase the ductility and therefore, the toughness. Area under the stress strain curve will be higher, with a minimum tensile strength of 1600 MPa is used for suspension cable in bridges. So, pre-stressing steel we have seen the usage of the other types of high strength steel in suspension bridges, and that's now it is clear why do we use this manganese, because it will make it ductile and this has to have high strength. Therefore, this is what we use, should have high strength, therefore, we use actually percentage of carbon is here higher, and then again they are cold drawn. So, that work hardened to get a very relatively high strength, and you can see that normal mild steel useful strength is about only 250 megapascal, that is what we use. We use reinforcing steel other, which will have about 415 or 500 MPa useful strength, proof stress 2% proof stress, but here we are trying to look at the strength which is about 1600 MPa. Of course, the useful strength would be this, and that is what is used for suspension cables in cable straight bridges. So, I think this should finish our discussion on structural steels. What is left is of course, the rebar, reinforcement bar, and that is what we will discuss in the next lecture. Now, in this lecture therefore, we have discussed structural steel, plain carbon steel, and there are various processes by which we improve this plain carbon steel or make them useful in different manner. Some of them we discussed in the earlier lecture, namely the strain hardening, and then we have now also looked into cast iron, and some utility somewhere they use some steel, special steel that or some steels that we use in specific use in construction, namely the pre-stressing purposes, and then tension cable in suspension bridges. That is what is it. Well, this is the usage of steel, plain carbon steel in nutshell or in brief in civil engineering construction. There are several other usage which we really did not discuss because it is outside the time limit of this course. So, there are several other usage which are there where we use steel in construction, right. Rebar is a special case which we will discuss at length. in one of our next lecture. I mean in the next lecture itself we will discuss rebar, use of rebar in steel at length. Okay. I think with this we can conclude this discussion. Thank you.